Okay, so today we're going to be talking about managing infrastructure as code. And particularly we're going to spend a lot of time talking about one tool, but we're also going to take a look at the history and provenance of some of the other tools in that space. The one we're going to spend most of our time looking at is a tool called Pulumi. Just before we get started, so I can get an idea of who's here and what people's backgrounds are, who considers themselves a developer versus an operator? So operators? One. Cool. Developers? Okay, everyone. That's good. Who has looked at infrastructure as code tools before and already know the background of them? So things like CloudFormation or Terraform or ARM templates. Okay, cool. That's a good number. Cool. So my name is James Nugent. You can find me on Twitter at Gen20, where once upon a time I used to tweet about tech, and now I talk about the infinite trash factory that is the UK government. So you can find me there usually. So the idea of infrastructure as code is a fairly modern practice. Right? So people were talking about it in the late part of the 2000s, and it came to prominence sort of in the mid-2010s as the adoption of cloud sort of increased significantly. So one of my favorite definitions of it is from Chris Munns, who's one of the evangelists at Amazon Web Services. And his definition is that infrastructure as code is a practice in which infrastructure is provisioned and managed using code and software development techniques, such as version control, continuous integration, and delivery. In other words, taking all the good stuff that you would normally do while writing applications and applying it to infrastructure code. So let's pull this apart a bit. The first important word in here really is code. And how we think of that depends on the background. Now, this is almost exclusively a room full of developers. So probably people think of programming languages, right? So Ruby, Python, F#, whatever programming language background you come from. Some people think of domain-specific languages in this case. So a lot of people who come from an operations background tend to think of the domain-specific languages that, around Puppet, or some built with Kotlin or Boo or any of the domain-specific language frameworks. Out of interest, who here's code and thinks YAML? Excellent. This is going to be fun. So the second part, so even if we, a lot of the tools in the space tend to use configuration languages. And the problem with that is they tend to mean that you can't do the second part of this definition, which is applying software development techniques, because you're not really writing software. What you're doing is writing configuration scripts. And as an industry, we've sort of understood in the software development world the value of being able to use good development techniques. Right? We can build abstractions, and we can deliver correct software, and we can scale teams that do that. And that same thing has not spread to people doing infrastructure as code. So we look at the landscape a little bit, and some of the tools that are commonly found in the infrastructure as code landscape. They really sort of fall into a couple of different categories. Sort of from low level to high level, we have things that provision cloud or physical infrastructure. So that's things like AWS VPCs, all the way down to physical switch configurations or router configs. And then sort of slightly higher level than that, we have managed services. So things like managed databases or managed container runtimes or managed databases. Moving further up, we have on-host configuration. So these are things, this is things like managing SSH keys or managing which packages are installed, SSH certificates. And then finally, as we move up, we have application configuration. So things like database credentials, service discovery, service configuration. And it tends to be that the tools that exist in this space fall into one of two categories, although there's some creep between them. But they tend to either work in the bottom two things of these. So this is tools like CloudFormation, Azure Resource Manager, Terraform. There's a whole bunch of these things, including Pulumi. Or alternatively, they fit into the top half. These are the ones we're not going to talk about too much today. There's been some good talks about various different pieces of this technology at this conference. In particular, one worth watching if you need to go back and find out more about this is the talk that Seth Vargo did about HashiCorp Vault, used for configuring applications at runtime. But we're going to spend most of our time today talking about the bottom two of these, so infrastructure, serverless, and managed services. So most of the tools that we just mentioned use some form of domain-specific language, either built on top of a programming language directly, or its own language that's been written from scratch. So here's some examples. This one is some chef code. It's clearly a domain-specific language kind of arrangement, but it's also written using Ruby, so you can see some of the standard programming constructs like standard library functions can be used here. And then if we move on to CloudFormation, which is the Amazon Web Services sort of built-in native infrastructure as code tool, that one tends to use either JSON or YAML, and looks a lot different because it's effectively just configuration rather than a program. And then there's Terraform. Are people generally familiar with Terraform here? Cool, okay. A few people. So Terraform uses a different configuration language called HashiCorp configuration language, which is not based on a language runtime like Chef's, for example, so you can't use Ruby or any other language's standard constructs. And instead you get this sort of interpolation system that allows you to call some limited range of built-in functions. So what I used to work on Terraform. I spent 3 years working on it, I guess, full-time. And we'd regularly see issues like this that would come up. So things like support use cases with conditional logic, because it turns out it doesn't have an if statement. The language that Terraform had was you declare what you want the result of something to be, and that's it. There were no looping constructs, there were no conditionals, there were no, it was a very much simple configuration language. So issues like this would appear. If you look back on enough of them, you can find me confidently telling people that you don't really want that because it's a terrible idea back in 2016. I guess you live and learn. This was another good one, so that was the simple one. That eventually got added, actually. Conditional logic got added. Loops eventually are being added to Terraform. This was a more esoteric one to embed the Lua interpreter so that you could write Turing-complete templates. That one's still open, but it's tagged thinking, which probably means it's never going to happen. But actually, you can see, like in some of the replies for this, it sort of boils down the difference between all these tools. And this was a quote from one of the replies to one of those issues that came around Terraform's sort of limited language, if you like. It said it was important from the beginning that Terraform's configuration language is declarative. So we've avoided adding flow control like conditionals and loops. So what does declarative mean? So as it's a room full of programmers instead of a room full of operators, probably most people already know this, but the difference between an imperative model and a declarative model is a declarative model, you say what you want, and in an imperative model, you say how you want it to be done. So if we look at a concrete example here, this is some code that creates a VPC in Amazon Web Services. So on the left, we have it written in Bash in an imperative style, using the AWS CLI. And on the right, we have a declarative model of it, written using Terraform config. So on the left, we can see you get the precise set of commands needed to go create this thing. And on the right, you have a declaration of what you want the end state to be, and the program goes and works out how to get there. So in this case, we're executing commands directly. In this case, we're providing rules that something else evaluates. So ostensibly, these are similar amounts of code, right? So it doesn't look like too big a difference. The problem is, like, you can't just run this twice. If you run this twice, it will create you 2 VPCs. If you run this twice, on the right, it will tell you that it's already in the correct state, so it doesn't need to go and do anything to get it into the correct state. So effectively what we're doing is building a model of what we want our system to look like, and then letting something else go and evaluate the real world and what we want, and then working out how to get there, versus giving instructions of exactly what commands to run. They end up calling the same APIs for the most part, but it doesn't necessarily have to. So what we really want is a model that bridges the gap between imperative and declarative. We'd like to have the full expression of an imperative programming language, but we'd also like to constrain the capability of it so that we can have a declarative model, ultimately, which is executed by something that can converge on our desired end state. So let's look at that in more detail. So this is sort of a brief architectural model of what a tool such as CloudFormation or Terraform looks like. Because I know Terraform pretty well, this is kind of what Terraform's internals look like at a very simplified level. You have a configuration parser, which reads the configuration file that was just up, and that builds a graph. So resources can link to other resources. You create one resource, and then you need to use a value that was computed as creating that resource as an input to another resource. So you get a big dependency graph of what has to be done at what time. And then you have an engine which takes the graph of what you want and takes the state of how it already is, according to the service, and works out a diff. So the diff is what is the difference between what's in the cloud now, in this particular case, and what I've said I want. And it comes up with a set of actions which are needed to get the cloud in question from the state that it's in now to the state that you said you want it to be in. And then there's some various resource providers which effectively provide a create, read, update, delete style interface to the remote cloud APIs. So you can imagine if we ran that VPC example we just had, it will get a single node in our graph, which is the VPC that you want. It either exists or doesn't exist in the real world now, or it could exist with some different properties set. So maybe we have to go change, like the CIDR block range or something like that. We'll get a diff out of it, and then we'll make calls through the AWS resource provider to the AWS API. So here's a question. What happens when you cross compiler engineers with this model? The founders of the tool that we're going to spend most of our time looking at are all compiler engineers from Microsoft. Worked on things like the async and await engine in C# and the F# language and TypeScript language and a bunch of other sort of low-level compiler constructs. So what you end up with is a model which looks very similar, but that can use any programming language to build the graph instead of a simple configuration language. There's a caveat on any programming language, which I'll come back to in a minute. But our model changes slightly, so it starts to look a bit like this. So rather than the configuration language making a graph, what you have instead is a program written in a real programming language, thin language host that just boots the program with the correct set of arguments and connects it down to the engine. And as the program executes, it registers resources that it wants as a result of its execution with the engine, which builds its own graph, and then execution basically proceeds in the same way. It works out a diff, and it makes CRUD operation calls through the providers. So let me come back to the caveat on this. I said it can use any language. That's not strictly true. It can currently use TypeScript, JavaScript, Python, or Go. There's some minimal amount of work needed to make a new language work. Some languages are more suited to this task than others. So .NET support's underway. There's some JVM support coming soon. It turns out that Go is not very well suited to it for reasons I'll explain in a bit. And JavaScript is not suited to it because it's not suited to anything. And Python and TypeScript are kind of the sweet spots, so you get to choose whether you want types or not, and obviously if you have the choice between types or no types, you choose types, so we'll choose TypeScript. So with that, let's take a look at how this stuff works sort of in practice rather than in theory. So I'm going to switch to, I'm going to try live coding in a language which compiles to JavaScript, which might be a bad choice, but we'll see. Okay, can everybody, do I need to make this bigger? Okay, so we'll make a new folder here and start a new project. So we'll do Pulumi, which is the name of the tool that does this, new, and then we'll give it a template name. So we'll use AWS in this case, and we'll use the TypeScript language. So running this, we'll go and create us a project and go and bootstrap some boilerplate code. Go and install the internet off NPM because it ultimately is still Node. So I can see the network monitor up here going crazy for a second. Okay, cool. So now we have, because it's again Node, we have the Node modules folder, which means tree is useless. So tree, ignore Node modules. Okay, we have this stuff. um, that was close enough, I guess. We'll get an IDE up, sorry, and go look at what the code looks like. So the thing that it generates for us just has some boilerplate code in it, and we'll delete that. And we'll go through and implement, a basic virtual network in Amazon. The reason I'm doing virtual networks is not specifically because they're better suited to this. It's just they're quick to create and they're free to create. And I've done this demo so many times now that if I was creating instances that cost money, then I'd be very poor. So I'm going to use free resources and quick resources. So effectively what we end up with, this package here, Pulumi AWS, exposes the entire surface area of AWS as an object model. And constructing objects declares that we want this resource to exist. So we go through and construct objects through the execution of our program, and that effectively adds graph nodes saying we want this thing to exist. So we could do new AWS, and then you can see the the surface area is sort of divided up into these namespaces. So VPCs live within EC2. So we have a VPC here, and we can give it a name. So we'll call it my VPC. And then we have to give it some arguments. So there are some things that have to be specified when you go create an AWS VPC. Things like the address space you're going to use, whether you want DNS enabled, that kind of thing. So we could, because we're in a proper programming language here rather than a configuration language, you get all the affordances of a programming ecosystem. So all of the IDE completion works, all of the documentation works, all the linting tools work, all that kind of thing. So we could do here, implement all members, for example, and all of this stuff just gets pulled out of the type system. So in this case, we'll say we'll have these things, and then we'll put in some values here. We'll say we want DNS turned on. We want that will do for now. So there's that's a program that if you just ran it on its own wouldn't do very much. If you run it under the context of this tool, it will declare that you want an AWS VPC to exist, and then do all the other bits to work out how to get that thing to exist and how to get AWS to match the state of what you said you want. So let's go run that. So the command we use for that is Pulumi up, which will scroll a lot more output. So I'll leave it down here for a second. So this goes and queries the state of my AWS account and decides, does this thing that you said you want to exist actually exist? And in this case, it doesn't. So we have this component that needs creating. You can see the name matches what we declared. And the plan here is to create this resource. Right? It doesn't exist. We have to go create it. So if we go look at the details, you can see all of the options that will be set. Some of these are defaults. Some of them are what we configured. So instance tenancy, there's a default thing for that, so that's what's come through. So we can say yes, we want to perform that update, and then it will go create the infrastructure. And almost certainly what I've just done is left it in US East 1, which means we get the latency of the Atlantic for us as well. Probably should have changed that to Europe, but it shouldn't be too bad. Okay, we're creating. Created, and we can see, this took 23 seconds. We've got two resources created. So one was the stack, which is the sort of the container for all of the resources, and then one was the VPC. And if we click on this link, we can see in the sort of the backend manager for this that we have. We can see the activity here. We ran an update on it. We can see all the details of it, so what changed, so you get some kind of audit control over who's done what with your infrastructure. You can go and see the resources, and does anybody here work with AWS on a day-to-day basis? Cool, so this is the most useful feature of the lot. For every resource, you can deep link into the console for it. And it will just open the UI for it, which is, it doesn't mean much unless you have to do it on a day-to-day basis, in which case this is like the most useful feature you've ever seen for anything. Okay. So let's say we want to go modify this infrastructure now. We have some kind of rule which says we're supposed to tag every object in our system so that you can track it for cost control. So you can specify tags. just a thing for that, and tags take a map or an object. So one of the things that's quite common to want to do in this kind of program is apply like some base set of tags to every resource and then override some specific ones on an individual resource. So we could say, okay, our base tags are going to be, we're going to apply this project name to everything. And then our VPC tags, we're going to use the nice JavaScript syntax of object.assign to create a new object that has all of these fields and then some new ones. So we'll say name demo VPC, and we'll assign that to base tags. And then we'll put the tags on this resource. So now if we go run our program again, we'll go and run our program under the context of the tool and work out what needs to be done to go and change the state of AWS into the state of what we've said we want. So in this case, we've seen that the diff is that we need to go and add the tags, so we need to update the existing resource. If we expand out the details, we can see exactly what we're going to do here. We're going to add this now two-field map of the tags that we want. Okay, so we'll just perform that update. So part of the benefit of being able to use code is that you can use standard code constructs. So for people who've used things like Terraform, the lack of looping is a big problem. You have to end up with all kinds of hacks around some code to avoid having to do loops. And we don't have the same restriction, though, if you have a programming language that you can use. So we could here assign the VPC object to a variable, and then go through and use that in further code. So we could say here we're going to create some subnets in our VPC. So in Amazon terminology, a VPC is a network container, and within that are various subnets which live within a particular data center. And each network has an address space which is a subset of this, for the most part, of the container address. So we'll say we're going to create 3 of them, and we're going to have 10, 0, 1, 0, 24. 10, 0, 2, 0, 24, and 10, 0, 3, 0, /24. So we want 3 of these subnets in 3 different data centers. Maybe we're going to run like console or a database or something in there. So because we've just got an array here, we can just go and use standard functional programming constructs. So we could say we're going to map this list of CIDR blocks onto a function. Well, we're using a function. And say, for each one of those, we're going to return a new AWS EC2 subnet. And we'll call it subnet index. So index is going to be the number of the position in the array of that particular address block. And then we have the same thing we have to do where we set some arguments. So one of the things you have to do with a subnet is say which container network does it live in? Which VPC does it live in? So we can start to build up object references in our code base. And because we have an object here that represents the VPC, we have all of the data about the VPC available to us. So here we can say VPC ID for the subnet is VPC dot, and then this is all of the information that you can that can exist about a VPC. So in this case, we're going to take the ID. And something else we have to provide is the network address space. So we'll give it the CIDR block. And then we can also give it the tags. So we can use the same style as we used above to create some tags specialized for these resources. So we can say object assign, name is public subnet index. So that will give them each a unique name tag counting from 0 to 2 in this case. And we'll assign that to base tags, and then it will get all the other ones that it's supposed to have as well. So what we've effectively done here is a looping construct, which many of these systems will just not allow you to do because it allows you too much power. If we go run our program, then what we'll find is, when US East 1 wakes up, is we're going to need to create 3 subnets, subnet 1, subnet 0, 1, and 2. to make the state of AWS match what we said we want our world to look like. If we go look at the details, we can see the VPC ID has been populated all the way through, the tags have been populated all the way through and constructed correctly, the address spaces have made their way all the way through, and we basically got what we expect. So there are some things missing from this. One of the things that's really useful to be able to do is make dynamic queries. So query the state of the world, and then adapt the infrastructure that you're going to provision depending on what your world looks like. So an unknown feature of AWS for most people is that availability zones are not sequential and not guaranteed to exist. So my account may have US West 1A, 1B, and 1C, but Rob's account may have 1B, 1F, and 1G. We're not even guaranteed to have the same number of availability zones accessible to us. So you can't take any single block of code and reliably run it in two different AWS accounts and end up with a deterministic result. So really you need the ability to go and query what the state of the world is before you go and make decisions about how you want to go and provision. So fortunately, because we're in a programming language, we can go do that. So I'm going to do a little bit of refactoring here. I'm going to factor this stuff out into a function so that we can use the async keyword. I'm just going to take all of this, put it in this function, and then call the function. Functionally exactly the same program as we had, it's just that everything's inside a function now, so we can use the await keyword. There's a JavaScript proposal up right now that would allow you to use await at the top level, but it's not implemented yet. So here, we know that we have 3 subnets that we'd like, but we have no idea how many availability zones we have. So we can go query that. So we could say availability zones equals AWS, and then we have a bunch of functions exposed via the API. So you can go query almost anything that exists in your AWS account using this, or you could just go make like a regular HTTP call using an HTTP client or any other client library that you want. So we can say get availability zones, and our arguments here are going to be something like state available. So what we're going to say here is we're interested in all of the availability zones in our account that are currently working. That means if we're trying to deploy and an availability zone is down, we won't try and deploy into it because otherwise we'll just fail. This ends up returning a promise, so we just need to go await it. But now we have the result of this available to us in our program. So when we go create our subnets, we could say availability zone, and we have the names of them available in a string array. So we could go index this, and we'll get the name of a valid availability zone for our account. So I could go run this in my account, Rob could go run that in his account, and we'll both be okay. If you were to hard code the names, that wouldn't be the case. You'd have to go configure them for every account that you want to target this thing at. One point of note there is that has an obvious crasher in it, because if there are only 2 availability zones and we've said we want 3 subnets, then it will crash because we'll get an index out of bounds. The obvious thing to do is, actually you need to decide at that point what you want to do. Do you want to fail because you can't possibly operate with less than 3? Or do you actually just want to say, well, we need 3 of these things, but we don't care if 2 of them are in the same data center, in which case you can just divide that by the length of the array, and it will just wrap itself around. So there's a bunch of options here that you can choose for how you're going to react to things. Because you've got the full power of a programming language behind you, you can do whatever you like. So that's kind of how it works at the basic level. That's declaring resources and making queries on the API and executing a program. That doesn't really get us, that brings us sort of closer to code, but it doesn't bring us closer to software engineering practices. So ideally what we'd like is the ability to apply some better software engineering practices to the infrastructure code we're writing. Anybody that's ever written these things before has probably seen you end up with like a giant single-use mess of YAML or HCL or whatever, all of which is single purpose, and none of which has any reusability built into it, none of which has any abstraction built into it. So, what we're going to do is we're going to go and make a bunch of queries on the API, and execute there's a construct in Pulumi called a component. It's purely JavaScript in this case, so different programming language different language hosts have their own abstractions available according to what the idiom in the languages are. But in this case, we could say we're going to declare a class, so we can say class myVPC, and have it extend this class called component resource. We give it a constructor, and the constructor is going to look a bit like a resource constructor. So we'll give it a name, which is a string. We'll give it some options, or some arguments, which are going to be something. We don't know what they're going to be yet, so we'll just say any. And we have some options we can set, so we'll say that's going to be a resource options, which is a type from the library. So the first thing we have to do is just call, give this a name. So we'll call this a myVPC, and then we'll pass down all the other bits. And then we can go and start creating resources in this component. So we could say we're going to take out our VPC here. We're going to take out our subnets. Guess I better move the tags around because otherwise the program will fail. And I'm just going to ignore availability zones for a second. So what we've done here is just built a small component that represents a reusable piece of infrastructure. So we can start parameterizing this. So let's say we're going to declare an interface, which is a TypeScript way of describing the shape of an object. And we'll call it myVPC inputs, and we'll say we'll parameterize the address space, or actually we'll parameterize the name. That's going to be easier. So we'll say project name is an input of string. So unfortunately, being able to write code in a programming language doesn't remove you from the actual model of how this code executes. So every time you're somewhere in the program, every value that you touch may be something that's been specified in the program. It might be something that the cloud provider will calculate for you at some future point in time, or it might be something that your own program calculates at some point in future in time. So you really need some way for languages to be useful at this, to abstract across all three of those things and say, we might have a value, we might have a future value, or we might have a promised value. The future value being, they sound kind of similar. An output meaning something, by a future value I mean an output, which is something the cloud provider tells you, and by a promise I mean something that's calculated in your own program. So if we look at the definition of what an input is, hidden in the mess of generics up here, an input is either a T, or a promise of T, or an output of T. For people familiar with C# or TypeScript, that probably makes some sense. For any given type, we can either have the value available now, we can have it available in future, or it can come from somewhere else. So we get to use this construct everywhere for declaring different types. And now we can make our arguments of type myVPC inputs, and that will pass type information through. So here we could then go and use our value here instead. Okay, at a simple level that will work. So now what I can do is reuse this component and just instantiate it as many times as I want, right? So we could say VPC1 equals new, what did it call it, myVPC. And project name is going to be build stuff 1. And then down here, we can just instantiate the whole thing again. Build stuff 2. And now if I go run the program, barring any obvious typos that I've missed, we're going to get a slightly weird plan here because we actually have some resources existing from the last time we ran this program. So what that's telling us is actually that you can't do quite that because we have to make all of the names unique. So what we're going to have to do here is prefix all of the names for our component resources with the name of the actual component instance. And that should fix that. So if we run it up now, okay. So we can see here that what we're going to have to do is delete the original VPC that already exists, because that's not one of the ones that we specified we wanted. And then we're going to create 2 new ones, and we're going to create 3 subnets for each of those. Now that's fine, it doesn't give us much in the way of structure. It would be a lot more useful if we could impose some more structure on this thing. Right? So if we could link the subnets to the VPC to give a much clearer indication of provenance in the preview. So we can specify the parent of each resource to be a different resource. So you can sort of build this tree of dependencies, which isn't necessary for tracking resource dependencies, but it's very useful for tracking sort of the visual element of it. So now if we go run our plan with the parent set, there we go. We can now see which subnets are associated with which VPCs in exactly the correct way. So that gives us some sort of level of basic abstraction. Now a lot of tools allow you to do this with other sort of techniques. So Terraform has modules, CloudFormation has includes. Something that you'll find is not possible to do with most systems is package up and easily distribute different pieces of standard infrastructure. So let's say you're working in a company that has some policy which says your VPC may be configured in 2 ways. It may either be a public VPC or it may be a private VPC. They're the only 2 options you're allowed. You're going to use our set of resources for it. So the operations team goes and works out what does it mean to be a public VPC, what does it mean to be a private VPC, and you can go and publish components for each of these, and we can just go and pull them in using standard software tools, right? So we've learned that if you want reusable libraries in software, you publish them as packages. So in this case, we could go and say npm install, and then I have a package that represents a complete VPC that's open source. So I can say that the name of it is this. So I can just go and install this entire modular infrastructure as an npm package. Okay. And then instead of instantiating this class, we can go and use the one from the library instead. So I'll just import it. So this one takes exactly the same kind of argument set. So we'll call this demo VPC, and then we have some arguments. We'll need all of those. So okay, so we can go through and just fill these out briefly. We'll give it our base tags. We'll create a Dynamo endpoint, which is a thing that allows private communication to DynamoDB. We'll create an S3 endpoint, which does the same thing for S3. We'll say, a demo VPC. We'll turn on flow logs. We'll make it, demo.buildstuff.lt as its internal domain name. And here we have some options, right? We could either say we want 3 availability zones. But because we have the ability to adapt to our environment, it's quite common if you're in Amazon, for example, to want to say, well, depending on what region we want to go into, we want a different number of, we want to divide things up differently. So if we're in US East 1, we want 6 of everything because there are 6 availability zones. If we're in US West 1, we only want 3 of each because there are only 3 availability zones. So you can't really do that without the ability to go and execute arbitrary code during your process. But actually, we can do that with this. So we can pass in the sort of magic value per AZ. And when we run this, it will go and work out, okay, well, how many AZs do we have? So how big can our subnets be as a result? So let's go run this. I can actually delete all of this code now. So we've got down from, this is the extent of our program now. So we've pulled in a library package, and this is the extent of our program. If we go run this program, I think I'm in US East 1, so we have 6 availability zones in this particular account. So it will go work out, this one is a bit more comprehensive about all the resources it creates. A lot more comprehensive about the resources it creates. So it's going to be, yeah, we can start seeing here that we're going to end up with 6 of everything in effect. Well, there's the 5th one coming in, and where's the last one? Okay, it's kind of hard to see at this scale. There we go. We've got 6 of everything. And if we go view the details, we can see somewhere further up here, we can see, well, I know what I'm searching for here, so it's a /19. Okay, so here we're using, we've got 6 availability zones, so we need to divide our /16 address space into 6 chunks. Right? So we're going to use, for each chunk, we're going to have a public section and a private section, and we want the public section to be roughly a quarter of the size of the rest of it, of the private section. So we're going to use /22, and somewhere here we'd find /20s for the public ones. Sorry, for the private ones. So /22s will be the public addresses, /20s will be the private addresses. But if we're in, we change this, and we go and say we're going to deploy into US West 2 instead. Oh, Lumi config set. We go change the configuration. Well, actually, let's do EU West 1, and that will be a bit quicker. So EU West 1 only has 3 availability zones available to us. So if we try and divide our /16 into 3 instead of 6, we can have much bigger subnets. We have more addresses available to us. So now we're only going to get 3 of each thing here. And if we go and search for the CIDR address spaces, we're using /19s and /21s. This is the kind of stuff that's really hard to do when you don't have a programming language behind it, because to do this kind of CIDR math, you actually have to run code. So either you have to special case every little piece of processing that you might want to do on a value and build it into the tool, or you have to give people the freedom to be able to build their own functions. And that's exactly what this does. So that kind of covers the basic use case of this tool as a for creating resources and for componentizing things and being able to create some basic levels of abstraction. The problem is that's sometimes not the interesting level of abstraction. Right? Who here deploys into one cloud? More than one cloud? More than one cloud in the same project? Okay, a few people. So generally, cross-cloud is the kind of abstraction people want, right? They don't want vendor lock-in. What they want is the ability to what people generally want is the ability to take a single program and run it in lots of places, right? You want to be able to run a program. You want to take a program, run it in Amazon. If Amazon decide they're going to put their prices up, I mean they never will, but that's fine. Apparently, people believe they will at some point. Maybe you can start competing with Amazon, so you decide you don't want to pay them anymore, so you're going to move to a competing cloud. What you don't want is to have to go and rebuild all of your infrastructure for that. There's a second competing thing, which is it's quite nice to be able to use serverless stuff. In particular, it works really well as cloud glue, even if it doesn't work particularly well for running applications in. Although there's some workshops tomorrow that I think will probably disagree with the idea that it isn't very good for building applications. It's becoming a lot more useful. So serverless is this idea that you can build functions as a service, you can build functions and host them in a service, and you don't have to deal with application binaries, containers, virtual machines, anything like that. You pay per execution of the function, and they generally run very quickly and cost very little. So I think AWS Lambda gives you several million function executions for free every month before they even start charging you. And for low volume stuff, this is a really effective way of building, in particular, infrastructure glue, but also some applications. The problem is you tend to get locked into one or the other, right? You build an application for Lambda, you can't just take the same code and apply it to Azure or Google, right? Even though they all have basically the same set of services available to you, they all have a column database, they all have bucket storage, they all have functions available, they all have an API gateway. There's nothing really portable between them. So, because you can now build library abstractions, you can start to go and build abstractions that, rather than just moving sets of components within one cloud, can move entire frameworks between multiple clouds. So there's this library up here, for example, called Pulumi Cloud, that kind of abstracts the sort of lowest common denominator set of resources between different clouds. So in this case, we're using this abstracted API, so a cloud.table. And then what we're saying here is that once per day, we want to run this function. So anyone that's dealt with serverless on tools like Terraform or CloudFormation will know that the general way this works is you go write your code in a file, you compile it down, you have an entire build process, and then your infrastructure as code software kicks in. It picks up the build artifact and then goes and deploys it out to the cloud. So this kind of changes that model a bit. So this kind of program puts the actual code that will execute inside the definition of where it's going to execute. So this daily function here, so on hour 0 and minute 0 of every, on minute 0 of every hour, I guess. No, daily, okay. At midnight every day, this function, this Lambda function, is going to run. So that's not something that AWS has the ability to do. But just using the tools available in a programming language, we can say we can take this entire block of code, work out what it depends on, serialize all of its dependencies as a Lambda function and all of the accoutrements of a Lambda function, and create them via the same mechanism we were just creating VPCs. It's kind of magical when you look at it. I'm going to pull up an example of it. The one I'm going to pull up is a URL shortener. This is kind of a really simple service. It has an API. The API is a sort of an API gateway. It has a DynamoDB table if you're in Amazon. And then we start defining routes on our API. So normally this involves a bunch of resource glue that you have to go and stick together. But we can just say we're going to get, for /URL here, we're just going to execute this function and build the entire thing as if it were real code and a real framework. So if we go install all the dependencies, because node. It really does download a lot of dependencies, huh? Okay. So bear in mind that program didn't mention a single AWS resource, right? It didn't talk about Dynamo. It didn't talk about API Gateway. It didn't talk about S3. You have to tell it which region we want. So the program talked in generic terms, right, about bucket storage and about database table storage and about API gateways. But via the same abstractions that we can use to declare component resources, we can go through and expand this out into what it means for that particular cloud. So in this particular case, the API gateway, it had several routes with it. Each route for an API gateway in AWS ends up with a separate Lambda function. So it's expanded out into several different AWS Lambda functions, each of which has its own role and security context associated with it. We also have a bucket that has some static content in it, and all of the objects in this bucket which are served off the local file system, and the various bits to make the API gateway work. The beauty of this is that we didn't mention in the program anything about the AWS services here, right? The only time that AWS appears is up here. And if we were to happen to change that to Azure and go and reinstall the dependencies and rerun the program, this would just run unchanged in Azure. Instead of being DynamoDB, it would be Cosmos DB. Instead of being AWS API Gateway, it would be Azure API Management. Instead of being S3, it would be Azure Bucket Storage or whatever it's called, blob storage. But the point is, now you have, just by having the simple change to the process, of being able to write actual code instead of configuration. You can go and enable all of the regular abstractions that you might normally write and make them available in a pretty easy to consume package, at least I think. Unfortunately, I've run exactly out of time. If people have questions, I'm going to be around for the rest of the conference, which is 10 minutes. I actually here all night and all weekend as well. So if anybody has questions or comments about this, then feel free to either email or grab me in person or anything like that. And with that, thanks for listening, and I hope you enjoy the keynote and the end of the conference.